Hi everybody, and welcome to part 3 of our thermochemistry notes, where we are going to be talking about what's known as the enthalpy of reaction, also known as the energy of reaction, or in other terms, just talking about how much energy is involved in a chemical reaction. So let's get a couple terms down first. Calorimetry is the process used to determine the amount of heat within a substance. Oftentimes, you will hear these terms as far as food goes or a reaction. All right. A calorimeter is an insulated device used to measure the absorption or release of heat in a chemical or physical process. Really, a calorimeter is just really any insulated device. So in our lab, we're going to be using a styrofoam cup. All right. A thermos would work. Any of those can be considered a calorimeter. All right. Oftentimes, we use water to help us determine the heat or enthalpy of a reaction. All right, so changes in temperature of water can be used to determine this heat of reaction. Let's look at an example. A chemical reaction takes place in 25 milliliters of water that's at 25 degrees Celsius. Calculate the enthalpy change during this reaction if the highest temperature reached is 32. So you have a certain amount of water that was at 25 degrees, it went to 32 degrees. I want you to calculate the amount of heat that generated. Okay, so this is just simply a specific heat problem where we know that our heat is equal to our mass times our specific heat times our change in temp. All right, I gave you 25 milliliters of water. It's important to remember the density of water, all right, is 1 gram per milliliter. So if you have 25 milliliters, that means you have 25 grams of water. Your specific heat of water is 4.18, and that's in joules over grams times degrees Celsius. You ended up at 32 degrees. You started at 25 degrees. Remember, you always want that delta T to be a positive number. Okay. When you go on ahead and you punch that into your calculator, you find that whatever this chemical reaction was, it ended up giving off 731.5 joules of energy. So this is how you can just simply use specific heat to figure out, all right, the amount of energy a particular process gives off. You're going to be doing this in your lab that we're doing this week as well. Okay. All right, so let's expand this and see, once you know the heat or the enthalpy of reaction, it can be used in a factor label problem. So let's take a look at an example. Calculate the amount of heat required to decompose 25 grams of sodium bicarbonate. I have given you a balanced reaction along with what we call a delta H, or the enthalpy of reaction. This should be a delta. Remember, I just can't type in triangles. So delta H, and this is positive 129. When we're dealing with delta H, which remember delta H is called the heat or enthalpy of the reaction. Okay. When we're looking at this delta H, okay, it's either going to be positive or negative. Positive tells us that it is endothermic. Negative tells us that it is exothermic. A little reminder from a previous unit. All right, so how am I going to use this? Well, this correlates with your balanced equation. All right, for every 2 moles of sodium bicarbonate, you need 129 kilojoules of energy for this reaction. Well, I don't have 2 moles, I have 25 grams. So let's do this in a stoichiometry problem. So I have 25 grams of NaHCO3. I want to know heat, so that's an energy measurement. So I'm going to end in kilojoules. Well, I'm going to change just like I would with any stoichiometry problem. I'm going to change to moles. All right, so in 1 mole, all right, for sodium bicarbonate, you're going to find the mass from the periodic table, okay, and that is 84 grams. Okay, and that is of NaHCO3, sodium bicarb. I'm then going to do a mole, and instead of a mole to mole ratio, I'm going to do a mole to energy ratio. So balanced equation, I have 2 moles of sodium bicarbonate. So I'm going to get rid of those so they go on the bottom. For every 2 moles, I need 129 kilojoules of energy. Okay, you're going to go ahead and multiply the top, divide it by the product of the bottom, as always. And just to check my work, I will go on ahead and do that. So 25 times 1, 29 divided by, using those parentheses in the bottom, 84 times 2, close my parentheses up, and I get about 19.2 kilojoules. Okay, great. All right, you can go ahead and pause the video and try this one on your own if you would like. All right, so let's take a look at this one. How many kilojoules of heat are required, are produced, because this is a negative, so you're producing that energy, when 55 grams of iron 3 oxide reacts with excess carbon monoxide. So here's my balanced equation. So I'm starting with 55 grams of Fe2O3. I'm going to change those to moles. 1 mole of my iron 3 oxide is 159.8 grams. Okay, I'm going to be doing a mole to energy ratio here. I have 1 mole here, so 1 mole of Fe2O3 for 26.3 kilojoules. Okay. Now, as far as this sign goes, it is really important, but in this problem, I've already told you that the energy is produced. So you're just going to give me a number that's positive for this because it's implied by the question. And when we punch this into the calculator, you're going to go 55 times 26.3 divided by 159.8. And that gives us 9.05 kilojoules. Because it asked how much heat is produced, that is produced. We know it's produced because it is exothermic. Okay, great. All right, so it's really nice when you have a balanced equation with this delta H, but sometimes we don't have that. So that means that we're gonna have to do, not necessarily, sorry, my camera's a little shaky there. Hopefully we're back. Just gonna double check on my camera here because I hit it by accident. Yeah, we're good. All right, sometimes, you want to know the heat of reaction for a particular substance without actually performing that reaction, or you can perform the reaction and it's just too difficult to actually measure the heat of reaction. So instead, what we can use is what's known as Hess's law of heat summation. And this tells us that if you add 2 or more thermochemical equations to give a final equation, then you can also add their heats of reaction to give you a final heat of reaction. So let's see what I mean by that. All right, calculate the heat of reaction for the following. This is the reaction we want, and we want to know what the delta H for this is going to be, but we don't have any other, I don't have any direct information for this. Instead, I'm giving you 2 other equations and their delta H's. Remember to change my give me triangles there. And I've given you these delta H's. Well, we need to see if these 2 equations can add up to this one. And what I mean by add up is, let's look at this and we want to see if we're going to have the exact same things on the left and the right of the equation. Well, I have carbon here on the left and carbon on the right, so they're going to actually cancel out. I have 2CO, well, I have 2CO there. I have O2, well, I have O2 there, and they're both on the left side of the arrow. I now, on my right side, on my product side, I have 2 carbon dioxides. Well, carbon dioxide, that's 2 carbon dioxides. That checks off. So these 2 equations actually do add up to the overall equation I'm looking for. So when that happens, you're in good shape and you can just simply add these 2 delta H's. All right, making sure you do keep the signs for these. This is very important that you do keep the signs. All right, so negative 172.5. So I just added those up and you get negative, well, here we go. It's negative 566 kilojoules when you add those 2 up. So the delta H for this reaction is negative 566 kilojoules. All right, great. Well, that was nice and easy, but really not super interesting. They're not always that easy. Sometimes you have to manipulate the equations a little bit. So let's take a look at our next example. Barium oxide reacts with sulfuric acid as follows. So here's the overall reaction I'm looking for. And I want to know what the delta H is for that. Here are the 2 equations that I am giving you. All right, and you want to see if they're going to add up to this one. Well, sometimes you have to flip the given equation to fit your equation. And that's fine. And by flip, I mean make the products the reactants and the reactants the products. So let's take a look. Why would I do that? Well, I want to make sure as I look through that these add up and that things add up the way that I want them to. Well, I start with this. Barium oxide's on the left, barium oxide's on the left down here. So that's good. Sulfuric acid is on the left. Oh, sulfuric acid is on the right down here. So what that means, okay, is that I'm going to actually rewrite this one. H2SO4 is going to give me SO3 plus water. I'm going to cross this off and I'm going to change this sign. It's no longer going to be negative. It's going to be positive because I now have the reverse of the reaction. Totally fine to do that, but make sure that you change that sign because that's really important. All right. So again, we verified barium oxide's good. Now sulfuric acid is good. All right. My water is fine. My barium sulfate is good. Now, also notice I have SO3 here and SO3 here. There's no SO3 in my equation, but that's okay because this is left side and this is right side now, so those cross off. As long as they cancel out properly, you are good to go. So now again, I'm going to add these two up, remembering that I changed the sign. This is now a positive 78. So I have negative 213.4 plus 78.2. All right, and that does give us negative 135.2 kilojoules. So my delta H for my overall reaction is negative 135.2 kilojoules. Okay. These Hess's law problems really can be a lot of fun. They are a puzzle to solve. I'd like you to pause the video now and give this one a try. All right, in this one, you're doing not just the flipping and the adding up, but also sometimes you're gonna have to multiply based on the final equation. So give this one a try. I will obviously go ahead and do this one for you as well, but if you'd like to pause and try, that would be great. Okay, so let's take a look. Here's my overall. And I am looking for my delta H for this one. Okay, so just like we did before, we're gonna first align the equations based on the reactants and products. So I'm just gonna start here. I have iron on the left. Oh, well, I can tell down here already, I have iron on the right. So I'm gonna have to flip this, which is fine. So now I'm gonna have 2Fe, okay, plus 3 CO2. Is going to give me Fe2O3 plus 3CO. So I'm going to cross out what I'm not using anymore. It's important to do that. Otherwise, it's really easy to get confused. I'm going to change that negative to a positive sign. All right, so that's looking good so far. All right, so my Fe is on the correct side. Carbon dioxide I don't see in the overall reaction, so I'm going to not worry about that right now. My Fe2O3 is on the correct side, so that's good. All right, next thing I have to check is my O2. Okay, my O2 is on the correct side. So that's all great. So I have aligned my equations. Now, if you've noticed, things aren't really working out number-wise. So when that happens, you can multiply an equation to match up the overall equation. So let's take a look. Okay, so I have 2Fe, not a problem. Then I have 1.5. Now you might be thinking, this is a little odd. Why do I have halves? You told me a long time ago I shouldn't have halves in my balanced equations. And I did tell you that a long time ago. But in thermochemistry, sometimes this happens and you will have a half. So just kind of realize there's nothing crazy about that. It does work out. All right, I have 1.5 O2 down here, but I only have a half here. So that's not okay. So what I need to do is I need to multiply, all right, to get this to be 1.5. All right, so what times half is going to give you 1.5? You're going to multiply this whole thing by 3. And that's fine. You're going to go 3. Okay, so 3 times this. But if you multiply the equation, you also have to multiply the delta H. So just realize that that is something you're going to have to do. So that now gives us 3CO plus 1.5 O2 is going to yield 3 CO2. And remember, once you've done something, cross it off. All right. I usually don't rewrite this. I just do this in my calculator as far as the delta H, but that's really up to you. All right, so now let's see if this all works out. So now I'm just looking at what I've written in pencil, just for ease of seeing it. Okay, I wouldn't expect you to do this every time, but I'm just gonna rewrite what I have here. All right, and I know this takes an extra second, but that's okay, just because it's a little easier to look at. Okay. And all I'm doing here is rewriting this. My delta H for the top now is plus 26.74 kilojoules. My delta H for the bottom is whatever negative 282.96 times 3 is, and we can do that in our calculators later, okay? All right, so now I'm gonna check to make sure everything works out. Okay, so 2Fe, I have 2Fe, fantastic. My 3CO2, well, that's not in my overall, so it should cancel out, and it does, canceled out, great. 1.5 O2, great, that is exactly what I have, it's right there, perfect. Okay, then I have Fe2O3, great. Well, I have 3CO on the right and the left, so they cancel out. So what you're left with here is 2Fe plus 1.5 O2 is yielding Fe2O3, which is what we want to look, is what we want there. So let's go on ahead and put this into our calculator. So I have negative 282.96 times 3, and I'm going to add to that 26.74, and I get as my final answer, my delta H is, always having that sign, negative 822.14 with a label kilojoules. Okay. All right, I hope you enjoyed these thermochemistry problems, and you're going to get a lot of practice on it. So have a great day.